So as an investigation, we're going to consider the graph of f of x equals 2 to the power of x, and then we're going to consider its inverse to that graph, which is y equals f negative 1 of x. So if we were to set up this table of values, we graphed this as our base graph a couple days ago. 2 to the negative 3 gives us a value of 1/8, 1/4, 1/2, 1, 2, 4, 8, 16. So we have a good idea of what this exponential base graph function looks like. Just take a minute to sketch it. Okay, so if we sketch this exponential function, it's going to look something like this. Okay, and so now from this exponential function of y equals 2 to the power of x, we are now going to graph its inverse function. So let's recall what our inverse function looks like. So back to our transformations unit, our inverse function is a reflection in the line y equals x. So if I were to sketch the line y equals x here, just draw it as a dotted line. Okay, so we are going to reflect this into this line. And also recall that the inverse function, what we want to do is we want to interchange the x and y values. So as a table of values, my y values become my x coordinates. And my y values and my x values become my y values. Okay, so when x is 1/8, my y value is a negative 3. When x is 1/4, it's a negative 2. 1/2, it's negative 1. At 1, it should be 0. At 2, it should be 1. At 4, it should be 2. At 8, it should be 3. So we can visualize this graph to look like this. So this is our inverse function. And so recall also when we write the equation of our inverse function, we want to interchange our x and y values just like we do with our points. And so the equation becomes x equals 2 to the power of y. And so at this point, this is where a logarithm is going to be introduced, because in order to solve this equation for y now, I cannot get a common base between x and 2. That's impossible. So what we want to do is we're actually going to change this from an exponential form to what we call a logarithmic form. And so our logarithmic form is going to be the log with the same base value of this exponential function of x, and it's going to always equate to the exponent value. So the logarithmic function is actually represented as the inverse of the exponential function. So this is y equals log 2 of x. So technically, a logarithmic function is actually the inverse function of its exponential function. And so that's how logarithmics are formed, and that's what logarithmic functions are. Okay? So this just reiterates kind of what we just talked about. Given the function y equals 2 to the x, we can write the inverse function by interchanging x and y, then solving for y. So x equals 2 to the y, but to solve for y, there's no way we can find a common base between x and 2, so we change the exponential function into a logarithmic function. So x equals 2 to the y can be written as y equals log 2. So logarithms also have a base similar to exponential functions. So log, this would be base 2 of x is how we read it, where 2 is the base of the logarithm. If you see a logarithm of the following, just y equals log of x, where there no base is shown, then this is a common base of base 10. Okay, so, and this is along with base e, which we'll talk about later, but your calculator will only calculate in two bases, which is base 10 and base e. So we're going to learn also how to change the bases of our logarithms so we can evaluate things on our calculators. So the characteristics of a logarithmic function will be the inverse of the exponential function. So thinking about log y equals log 2 of x, this is the inverse of y equals 2 to the power of x. And so y equals 2 to the power of x, remember, was an exponential growth, right? And so the characteristics is all the x and y values are just going to be interchanged. Here, the exponential function had a y-intercept of 1. Now the logarithmic function is going to have an x-intercept at 1. The exponential function had no x-intercepts. That means the logarithmic function is going to have no y-intercepts. Exponential function, the horizontal asymptote was the x-axis. Logarithmic function, that horizontal asymptote should be the y-axis. The domain of our original function, or our exponential function, should be all real numbers. So that means the range of this function should now be all real numbers, right? Our domain and range are going to switch. So y is greater than or equal, or y belongs to the real numbers. The domain of this would be x is greater than 0. The value of c, just like here, is going to affect the steepness of the graph as x increases. And when c is greater than 1, so just like our exponential graph, we get what we call a logarithmic growth function. So this is a logarithmic growth. If our base is between 0 and 1, we get a logarithmic decay. So the characteristics of logarithmic functions are just the opposite or the inverse values of the exponential functions. Okay, so the next thing we're going to do today is we're just going to practice like converting from an exponential form to a logarithmic form and vice versa. And then tomorrow we're going to get into transformations with logarithmic functions. So convert each of the following from exponential to logarithmic form. So if I wanted to convert this to a logarithmic form, the base of my exponent will be the same as the base of my logarithm. So it's always log base 5 of whatever the exponential equation is equal to. That's going to become part of the logarithm. So it's a log base 5 of 25. And that's always going to equate to whatever your exponent value. So log base 5 of 25 equates to 2. Here, this would be log base b of 10 would equate to 3x. And c, this would be a log base x minus 2 of b equates to a negative 3. Okay, so that's how you change from exponential to logarithmic. And then vice versa, how do we go from logarithmic back to exponential? Similarly, whatever your logarithm is equal to, that becomes the exponent of your power. The base of the logarithm is going to be the same as the base of the power. So this would be 3 to the power of 3 equates to 27. This would be b to the power of n equates to m. And lastly, this would be b to the power of a to the power of c equates to y. Okay, so over time we want to be able to start to evaluate some of these things in our head, but initially we're going to do a little bit of algebra work in order to actually evaluate this. And we want to try to evaluate this without using our calculators. And technically our calculators won't do a log base 2, but I think the fairly new calculators will do any log base, any base logarithm. So what you want to think about is, if I were to change this back to an exponential form, this means 2 to some power is going to equate to 32. So 2 to some power is going to equate to 32. And so writing this back into an exponential form, now this allows me to actually solve this using just solving exponential equations. So I'm going to change 32 to a base of 2, which would be 2 to the power of 5. So that tells me this will equate to 5. So what you want to think about is, you're thinking about 2 to what power equates to 32. So when you're evaluating a logarithm, you're actually solving for the exponential value on the exponential equation. That makes sense. So same thing here. This means 4 to what power equates to 1/4. So again, if I reciprocate this and write this as a base of 4, would be to the -1. So this tells me that this logarithm, log base 4 of 1/4, is going to equate to a -1. Okay, similarly, okay, 6 to what power would give me a √6. So if you can't do that, start to do that in your head, then you're always going to set this expression up. 6 to what power equals √6. Well, technically I'm going to change this so it's a base of 6, not √6. So I can change this to an exponential form where the exponent is going to be a rational exponent. So log base 6 of √6 would equate to 1/2. So 1/2 would be my answer. Okay, something a little trickier. We have a logarithm as the exponent of this power. So I'm going to evaluate this logarithm first. So log base 4 of 16. So we're going to try and do this in our head now. Log base 4 of 16. So it means 4 to what power equates to 16? Well, I know 4 squared is going to equal 16. So log base 4 of 16 equates to the value of 2. Now I'm going to replace that exponent with a 2. 3 to the power of 2 equates to 9. So my final answer would be 9. Really, so we won't circle this 2 because that's not part of the question. Right? So our final answer should be 9. Okay? So similarly, right, if we are to solve this equation, it means 3 to the power of x is equal to 27. So 3 to what power equates to 27? So over time, you should be able to do this, evaluate this in your head. 3 to the power of 3 would give me 27. So here, fairly easy, x should equal 3. This question here might be a little trickier. 1/2 to what power is going to equate to 8? So if I set this up as an equation, 1/2 to what power equates to 8? So then what I'd want to do is I want to again change both of these bases to a base of 2. Well, this is going to become 2 to the negative x. The 8 is going to become 2 to the power of 3. So then what I have is a negative x equals 3. So x is going to equate to a negative 3. Here, this one's fairly straightforward. Remember, log base 5 of x is equal to 2. Evaluate for x. Well, 5 would be the base of my exponent, or my power. 2 would be the exponent, and then it would equate to x. So 5 to the power of 2 equates to x. So x would equal 25. And then finally, the base of my logarithm is x. So log base x of 64 equals 3. If I wanted to solve for x, x to the power of 3 equals 64. I am now going to take the cube root of 64. So my answer would be 4. Okay. All right, and then example 5. If log 2 of x is equal to 3 and log 2 of t is equal to x, then t equals what? So in this first logarithm, we could evaluate the x value. So if I change this back to an exponential form, the base of my exponent would be 2, 3 would be my exponent, and x would equate to x. So 2 to the power of 3 equates to x. So this tells me x is equal to 8. So now I have this log base 2 of t equals 8, because I've just solved for my x value. Now I'm going to equate for my t value. I'm going to change this logarithm to an exponential form. The base of my power would be 2. 8 would be my exponent, is equal to t. So 2 to the power of 8 equates to t. T would have to equal 256. Okay? And that is converting exponential form to logarithmic form and vice versa.